Welcome to communication course. Now, today we are going to see amplitude demodulation and single sideband and vestigial sideband. So let's start with demodulation of amplitude modulation. The process through which we are able to extract or reconstruct or detect the message or baseband signal from the modulated wave is known as demodulation. Demodulation can be classified in two types: synchronous detection, asynchronous detection. Now, uh, uh, the definition of demodulation actually says that, you know, in the transmitting end, we actually we have seen that in the transmitting end, we modulate the message signal with the high frequency carrier signal, and we uh, do some further processing and send that modulated signal by channel to the receiving end. Now, at the receiving end, when the modulated signal is received, now from this modulated wave, we have to extract the original message signal. We have to reconstruct or extract the original message from the modulated wave. So this process of recreating the message signal from the modulated wave is known as demodulation. And demodulation is occurring at the receiving section. Now, the classification, if I talk about the classification of demodulation of amplitude modulation, then demodulation can be classified into synchronous detection, asynchronous detection. Now, what is synchronous detection? We have seen that in amplitude modulation, we have seen double sideband full carrier and also double sideband suppressed carrier. So in case of double sideband full carrier, we are sending the modulated signal along with the carrier signal. So this carrier signal is known as a pilot signal. And why we are sending this carrier signal with the modulated signal? So that for the receiver, it will be easier to extract the message signal. So that because it has the information about the carrier signal, because we are sending the carrier signal with the modulated signal. So this kind of detection or demodulation is known as synchronous detection because we have carrier signal for detection. Now, we have seen double sideband suppressed carrier, where we are only sending the modulated signal, not the carrier signal. Okay. So when we are getting or receiving the double sideband suppressed carrier signal, then we are not having the carrier signal. So when we are going to detect the message signal, we have to do that without carrier signal. So that process is known as asynchronous detection, where no need of using carrier signal. Okay. Okay. So let's go to the next slide. So this is synchronous detection. So we have we already have some basic idea about this process. Now let's see. In synchronous detection, what we are doing, we are actually this is the receiving section. Okay, this block diagram actually shows the receiving section. So this is the receiving antenna. So in from this receiving antenna, we are receiving the modulated signal. So this modulated signal is xt cos omega ct. Xt is the message signal, cos omega ct is the carrier part. Now, we will send this modulated signal to multiplier, and at the other end, other input terminal of the multiplier, we will send the carrier signal cos omega ct. This cos omega ct can be locally generated or it can be pilot carrier. Now, pilot carrier means when we are sending the sending the carrier signal with the modulated signal. So in this both way, we can have the carrier signal. So the multiplier is multiplying this carrier signal and modulated signal. Okay. So after multiplication, we will get ET. ET means xt into cos omega ct into cos omega ct. So we can write xt into cos square omega ct. So this is the multiplication of these two signals. If we multiply these two signals, then we will get this. Then after multiplication, after multiplier, we will send this ET to the low pass filter so that the low frequency signal will be allowed and the high frequency signal will be they will be banned. They will not be allowed, okay, to pass. So the signal of omega c or fc will be cut off, and the signals which is less than omega c will be allowed. So xt is the low frequency signal, so xt will be allowed and this portion will be cut. So we will get half xt. Now how we are getting half xt? Let's see the calculation. So here is the mathematical analysis. So ET means after multiplication, we will get ET as xt cos omega ct into cos omega ct. Now, we can write xt into cos square omega ct. Now, instead of cos square omega ct, we can write 2 into cos square omega ct. Sorry, 2 into half into cos square omega ct, right? And xt is multiplied here, okay? So 2 will be nullified, and this equation is equal to this equation. So we can write this equation as in this form. Now, so it can be written like half into xt into 2 cos square omega ct. Now, this 2 cos square omega ct, we can further analyze this we can further analyze this portion using algebraic formula. Now, what is the formula? The formula is like 2 cos square a can be written like 1 plus cos 2a. Okay. So instead of 2 cos square omega ct, we are writing 1 plus cos 2 omega ct. So if you multiply this like half into xt into 1 plus half into xt into cos 2 omega ct. So we can get this. Now, if we take this in frequency domain, then we will get E omega is equal to half x omega plus 1 by 4. Now, we know that cos 2 omega ct can be written like half into x omega plus 2 omega c plus x omega minus 2 omega c. Okay, so this half is multiplied, so it becomes 1 by 4. Okay, so we are just applying the Fourier transform of cos 2 omega ct. Okay, okay. Now the spectrum, if you draw this E omega, then you will get this. So this is our E omega. Now, here in E omega, we are getting half x omega, then 1 by 4 x omega plus 2 omega c in plus 1 by 4 x omega minus 2 omega c. So we will get one spectrum at the center, then we will get another spectrum at 2 omega c and sorry minus 2 omega c, and we will get another spectrum at plus 2 omega c. So we are getting a spectrum at the center. So this is the center, and we are getting another spectrum at plus 2 omega c and another spectrum at minus 2 omega c. Now, after when you will pass this signal through a low pass filter, so this 2 omega c minus 2 omega c, they will be cut, and we will get only this portion. Okay, only this low frequency signal portion. So this is how we can get the half x omega. Okay, so this is how actually we are doing this synchronous demodulation. How? Just by multiplying the carrier signal with the modulated signal, we can get the original message signal. This is a very simple process. So this is known as synchronous detection. Now, carrier synchronization process. So this carrier synchronization process can be done by these two ways. One is pilot carrier, one is Costas receiver. So you know about pilot carrier, and we are not going to see Costas receiver in details. Just know the name of Costas receiver and why we are using this to generate the carrier signal in synchronous detection or synchronous demodulation technique. Okay, that's it. Now we have seen envelope detector or envelope detection in our lab. So envelope detection is asynchronous detection or asynchronous amplitude demodulation. So envelope detector is another way of amplitude demodulation. Now I have actually explained this circuit in our lab, but again, for your convenience, I'm explaining this in short, actually, in short, obviously. Now, okay, so in envelope detection, okay, in envelope detection, this is the circuit diagram of the envelope detector. So this is the input port. So in the input port, we are actually sending the modulated signal. What is the modulated signal? Say, for example, double sideband full carrier. So this is our modulated signal. So we are actually sending this signal as ST to this port. Now this is the diode, this is the capacitor, then a load resistor is connected here, and we are taking the detector output across this load resistor. So here we will get our V out. Okay. Now, let's understand the working of this circuit. So, when you will see the diode, you have to understand, or you have to get the point that if there is diode in my circuit, then this diode will work as forward bias or as reverse bias. Okay, for the time being, it will work as forward bias. For the time being, it will work as reverse bias. Now, if you have a capacitor in your circuit, then you have to realize that, okay, this capacitor will charge for some time period and it will discharge for some time period. Okay. So the function of the capacitor is charging and discharging. Now, when you are giving the input signal, so say for example, this is our input signal. So this is positive, okay? So this is positive. So at the starting, the capacitor will have no charge. So there is positive voltage applied, okay? This is positive, this portion is positive. So the diode, this is the P terminal and this is the N terminal. So the P terminal of the diode is connected with a positive voltage and N terminal of the diode is connected with, say for example, ground, because there is no charge. So the P terminal of this diode is positive in charge. So this diode will be in forward bias and it will work as short circuit. So when it will work as short circuit, so the positive voltage, whatever we are giving as input, this positive charge will flow through this circuit and it will go to where? To this capacitor. Now this capacitor will absorb the whole charge, and it will eventually be charged. Okay. So as the input voltage is increasing, the voltage across this capacitor is also increasing. So it is getting plus, it is getting minus. So this is how it is being charged, and the charge across the capacitor is like this. It is increasing. Now, when the input voltage tends to decrease from the maximum value, so this value becomes lower than this value, because the capacitor has absorbed the maximum charge, and this time the capacitor has a charge which is like maximum value. Now, when the input voltage crosses the maximum value and tends to decrease, the value of capacitor is larger than this, and this positive terminal is connected with the N type or N terminal of the diode. So here is positive, and this portion is less than this voltage, so this will be negative. Okay, here is also some voltage like this, and here is also some voltage, but this voltage is higher than this voltage. Okay, this is lower and this is higher. So this terminal become positive and this terminal become negative. So this diode will be in reverse bias, and whatever voltage is being applied in the input terminal, it will not cross this open circuit. So what will happen? So this capacitor now, for this time duration, when the input voltage is below the maximum value and it is negative, it is it is below the maximum value. Okay, for the time being, when the input voltage is below the maximum value, the voltage of the capacitor is higher and the diode is in reverse bias. So this is open circuit. So the capacitor will now start discharging, and it will discharge because this is open circuit. So it cannot discharge through this path. So it has another path here. So it will discharge using this path. Okay. So using this path, it will start discharging. So this is written discharging path. Now, when it will start discharging, so all the voltage will be across this resistor where we are getting the detector output. So when it is being charged, you know, this detector output, if I draw the detector output, V out, then how it will look like when the capacitor is charging, it is following the input signal. When it is discharging, it is slowly discharging. Then again, when the input voltage is crossing the maximum value, okay, this maximum value, again reaching this maximum value, then again, the voltage of this P side is higher. So again, this diode will be in forward bias. So the capacitor will again start charging. Okay, start being charged. Then again, when the input voltage becomes lesser than the maximum value, okay, then again it will be disconnected and the capacitor will be discharging. Okay, so this is how the capacitor is being charged and discharged, being charged and discharged. But if I draw the okay, so here you can see the figure clearly. The black line shows the modulated signal. The red line shows the output of the detector. Okay, so when the input voltage is being positive, the capacitor is charging. When the input voltage is less than the maximum value and when the input voltage is decreasing, the capacitor is discharging. Again, when the amplitude of the modulated wave becomes higher, like in this point, okay, in this point, it is getting higher than the voltage of the capacitor. So again, the capacitor will start charging. Then when the input voltage decrease or it is getting lesser than the maximum value, the capacitor start discharging. Again, when the input voltage becomes greater than the charge of the capacitor will start again charging. Okay, then again it will discharge. So this is how it is charging, discharging, charging, discharging, charging, discharging, charging, discharging. This is how it is just following the envelope of the modulated wave. So this is actually the envelope of the modulated wave. So this is actually the envelope of the modulated wave, and we know the envelope of the modulated wave actually represents the message signal xt. So there is you know, a little ripple, but if we use low pass filter or filter, we can get reduced from, or we can prevent these ripples. So we will get a smooth output voltage at the detector, and that smooth output voltage actually represents the original message signal. So this is how we can extract the message signal perfectly. Now there is an optimal condition for envelope detector. Now there are two conditions. Okay, so if you see, this is our capacitor, and we know the charging time and discharging time of any capacitor actually has a specific equation or formula. What is that formula? The formula is that when it is charging, we know that the charging time tau can be written like RC. Now, what is RC? R means the resistance of the charging path, the total resistance present in the charging path. So what is our charging path? So this is our charging path. This is our charging path. So the resistance present in this path is R, and the capacitor present in this path is C. So the resistance present in this path is written like RF. RF is the forward biased resistance. So the forward bias resistance of this diode, okay, this is actually known as RF. And there is some resistance of this circuit as well. So that resistance is referred as RS. So RS is denoted like the internal series resistance. Okay. So here we can get two resistance. One is RF, forward bias resistance, and one is RS, which is very minimal, which is very low, which is the circuit, the internal resistance of the circuit. Okay. So in charging path, we are getting RF plus RS into C. So this is our total charging time. Okay. So this is our total charging time. So the charging time is depending on the RF and RS and C. Okay. Now what is the discharging time? The discharging time of the capacitor is also written as tau into RC. Now this R represents the resistance of the discharging paths. Now the charging path and discharging path is not same. So this is our discharging path. So in the discharging path, we have only load resistance, which is denoted as RL. So this is charging tau and this is discharging tau. So this discharging tau is equal to RL into C. Okay. Now there is an optimal condition for this tau charging and tau discharging. There is an optimal condition for the charging time and discharging time. Now, why we need to follow this condition? Why we have this condition? Why there is a limitation on the charging time and discharging time? Because, see, say for example, so this is actually charging and discharging, right? Charging and discharging. So this is how it works. Now, if the discharging time, tau discharging time is very low. Okay, is very low. So discharging time is very low. What does it mean? It means that, say for example, the discharging time is 5 seconds. It means within 5 seconds, the capacitor fully discharges. And when the tau discharge is 2 seconds, it means within 2 seconds, the capacitor discharges fully. Now, if the discharging time is very low, which means the capacitor will discharge very fast. Okay, so it is charging but discharging very fast. Again charging but discharging very fast. So if it discharges very fast, so the output will be look like this red light. Okay, so there is very, it is increasing, decreasing, increasing, decreasing. So the curve, the overall curve is not following the envelope. Okay. So there is a difference between the envelope and the output wave. See, here there is very less difference between the output curve and the original message signal. Okay, because here the discharging time is very high. Okay, so the discharging time should be a bit high so that it discharges very slowly. Okay, again it charges and discharges very slowly. So it remain near to the envelope. Okay, it remain near to the envelope, charges but discharges, charges, discharges. Okay, so that there is very low ripple, very less ripple. So it will be easier to smooth this signal and get the original message signal. But if there is so many ripple, okay, so many fluctuation, then it is difficult to smooth this curve, smooth this signal and get the message signal. So the tau discharging should not be very low. Okay, it should not be very low. And this discharging time should be less than this half cycle. So see, this is the modulated wave. This is one full cycle of the modulated wave. Okay. So this is full cycle of the modulated wave, Tm. Now, what is the frequency of the modulated wave? Fm. We know that Fm is equal to 1 by Tm. So this discharging time, tau discharging should be higher than this half Tm. Okay. It should not be less than this half Tm. It should be higher than half Tm. Or we can write it should be higher than 1 by Fm. Okay. So the condition is that discharging time, which is Rf plus Rs into C, should be very less than 1 by Fc. Okay. 1 by, so sorry. I have denoted this modulated wave, this time period is actually the time period of the carrier signal, right? This frequency actually is the frequency of the carrier signal. So we need to write this Tc, and this frequency is carrier frequency Fc. This is Tc. Okay. So this tau discharging should be very greater than 1 over Fc. Okay. So this should be less than, tau discharging should be greater than, okay, this should be greater than 1. Tau discharging, it should be higher, than 1 by Fc. If it is less than 1 by Fc, discharging time, okay, give me some time. Discharging time should be mm, higher than 1 by x. Actually, I have explained this earlier. So, discharging time, this condition is correct. Now, discharging time is actually RLC. Okay, so this portion, I was actually talking about this portion. So, RLC should be higher than 1 by FC. Okay. Okay. Now, what is written about the charging time? Let's see what is written about the charging time. So, see, when you are charging, when you are talking about the charging, okay, when you are talking about the charging, so this charging should be it should be followed the amplitude of the it should be followed the amplitude of the modulated wave. Okay, so this charging time tau charging should be less than 1 by FC, or it should be less than 1 by FC means TC. Okay, now TC is the time period of the modulated wave. So this charging time should be less than the time period of this modulated wave. Okay, otherwise it will charge very slow. Okay, otherwise it will charge like this. Okay, it will charge like this. It will charge very slowly. So we want to charge this along with the positive peaks of the modulated wave. So we need to follow this charging time is equal to almost half of the time period of the carrier signal. Okay, or we can write it should be less than the time period of the carrier signal. Okay, so time period is written as 1 by FC. So it is written like it should be less than 1 by FC. So this is the tau charging condition. Now again, there is another condition for discharging time. What is this? Now when you are discharging, so this is our modulated, this is our original signal. Okay, this is the envelope of the modulated wave. Now this modulated wave have some time period also. So what is its time period? Like it is going to positive, then negative, then again positive. Okay, so you can say like this is one time period. Okay, so the message signal has a time period as TM, and it has a frequency as FM, which is equal to 1 by TM. Okay, now if the discharging time is very high, okay, if it is very high, like if it is equal to TM, okay, then whatever when it is when the discharging time is very high, so it is being charged and being discharged in a very high time. So for that reason, it will not be able to follow these values in the modulated wave. So there will be some gap between this detector output and the envelope of the modulated wave. So for that reason, the discharging time should be low. It should be low than 1 by Fm, or it should be low than Tm. Okay. So it should be, this discharging time should be higher than Tc. It should be higher than Tc, but it should be lower than Tm. Okay. So this is the optimal condition for envelope detector. Now the single sideband. So the single sideband modulation is like, this is our spectrum of X omega. Now when you are doing modulation, you will get this portion, one shifted to omega c, one shifted to minus omega c. Now, if you pass this signal to a filter, okay, you have to pass this filter through a filter. Sorry, you have to pass this signal through a filter. So if you select the cutoff frequency of that filter, like it will only allow the portions which is greater than omega c, then only the upper sideband will be selected and the lower sideband will be cut off. The upper sideband will be selected and the lower sideband will be cut off. So this is how we can get only the upper sideband. Again, if we pass the modulated signal through a filter, through a low pass filter, which will only allow the signals which is less than omega c, then the low sideband will be allowed and the upper sideband, which is higher than omega c, will be cut off. So this is how we can get the lower sidebands. So if we allow only lower sidebands, then we can get the spectrum like this. If we have only upper sidebands, then the spectrum will look like this. So if we pass only one sideband, then this modulation is known as single side band amplitude modulation. Okay. Now, how we can do single sideband suppressed carrier? So single sideband suppressed carrier means we are not actually we are actually doing modulation without the carrier. So this is our message signal cos omega mt. This is our carrier signal cos omega ct. Now, if you do modulation, then cos omega mt into cos omega ct. So we are actually uh, 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 further, applying the algebraic formula and simplifying this line. So we can write half into cos omega c plus omega m t plus cos omega c minus omega m t. Okay. So we know that omega c plus omega m actually is the upper sideband and omega c minus omega m is the lower sideband. However, for SSB, we transmit either any sideband. Therefore, SSB with USB can be written as, so if you take the upper sideband, so you can write half cos omega c plus omega mt. Okay, so we are actually further applying another algebraic formula, and we are actually further simplifying this as half cos omega m cos omega ct minus sin omega m sin omega ct. Okay, so this is the formula actually, cos a plus b. So we know that cos a plus b is equal to cos a cos b minus sin a sin b. Okay. So the this is the formula for upper sideband. Now similarly we can write for lower sideband. So half cos omega c minus omega m. So we can further simplify this. So half cos omega mt cos omega ct plus sin omega mt sin omega ct. Now in general, SSB can be given by equation. So when we are getting LSB, here is a plus sign. When we are taking USB, there is a minus sign. So we can write a general formula, and for USB, there is minus sign. For LSB, there is plus sign. Okay, so we are actually writing plus minus for this general equation. Okay, so we can write cos omega mt, cos omega ct plus minus. Instead of sin omega mt, we can write cos omega m minus pi by 2 t sin omega ct. So what is cos omega m minus pi by 2 t? So cos omega m t is our message signal. Now cos omega m t minus pi by 2t, which means we are actually shifting xt. We are actually shifting xt by pi by 2. So we can term this shifted version of xt as xht. So we can write, instead of cos omega m minus pi by 2, we are writing xht. So half into xt cos omega ct plus minus x. So this is the general formula. This is the general formula for single sideband spectrum. So instead of sin omega mt, we are writing cos omega m minus pi by 2t. Now instead of cos omega m minus pi by 2t, we can write like cos omega m is actually the message signal xt. So if we get cos omega m minus pi by 2, which means actually xt, the message signal, is shifted by pi by 2. So if you denote this shifted version of message signal by xht, then you can write the general formula of single sideband suppressed carrier like half xt into cos omega ct plus minus xht into sin omega ct. So this is the general formula of single sideband. Now the power saving capability of single sideband full carrier over double sideband full carrier signal. So if you send the single sideband full carrier, means there will be one single sideband and also there will be a carrier. And what is double sideband full carrier? There will be two sidebands and a carrier. Now, what is the power saving capability of single sideband full carrier? Why we are attracted to single sideband? Okay, why we are studying single sideband? So there should be some reason as well. There should be some advantages. So here is one advantage, like the percentage of power saving of SSB over DSB signal is equal to power in SSB divided by power in DSB into 100%. Now, power in SSB means power in single sideband, power in one sideband, plus power in carrier. Now, power in DSB means power in both sideband plus power in carrier. We know power in carrier can be written like PC. Now, power in one sideband is PC into mu square by 4. And power in both sideband is PC into mu square by 2. So if you simplify this, you will get 83.33%. So the power requirement for SSB is less than DSB. So you can save 83.33% power in SSB. So this is beneficial for us. Now, maximum efficiency of SSB FC. So the power in one sideband, okay, power in one sideband, because the message we get only from the sideband. So the power in carrier is actually wasted. So the total input power is power in carrier plus power in one sideband. The output power is power in one sideband. So the power in one sideband can be written like PC into mu square by 4. Power in carrier is PC plus power in one sideband is PC into mu square by 4. So if we simplify this and place mu maximum equal to 1, then we will get 20%. So the maximum efficiency of SSB FC is 20%. If you recall, the maximum efficiency of double sideband full carrier is 33.33%. So the maximum efficiency of single sideband full carrier is less than double sideband, but the power saving capability of single sideband is higher than double sideband. Now the generation of SSB. The generation of SSB can be of two types, like phase shift method, frequency discrimination method. Okay. So frequency discrimination method we will see in our lab class, the next lab. Now we will only just learn about this name here. We will not learn the detail of these two method of generating single sideband. Now there are some issues of single sideband. So single sideband transmitter and receiver required an excellent frequency and phase stability because any shift may change then quality of transmission. So as you are sending a single sideband, so the receiver quality and sensitivity should be very high. Okay, so again, the SSB transmitter are expensive to design. So SSB suffers from difficulty to suppress one side
ম্যাম আপনার সাউন্ড আসতেছে না, আমরা শুনতে পাচ্ছি না।
হ্যাঁ, অনেকক্ষণ ধরে শোনা যাচ্ছে না ম্যাম।
Okay. Okay, now I think you can hear me. So I was muted. Okay. Okay, so the issues of SSB. So the SSB transmitter and receiver required an excellent frequency and phase stability because any shift may change then the quality of transmission. So in single sideband, the receiver should be of excellent quality. Okay, it should have excellent stability. So this is one problem. Then the SSB transmitter are expensive to design as SSB suffers from difficulty to suppress one sideband completely. SSB is used in mobile communication. So, when you are getting the single sideband, you are actually using a filter. Okay, you are using this filter, and for this upper sideband, you are actually using a high pass filter. So the cutoff frequency of that high pass filter is omega c. So the high pass filter will allow all the frequencies higher than omega c, and it will cut all the frequencies lower than omega c. Now, this filter should be of great quality. It should be of great sensitivity so that it will cut all the frequencies lower than omega c. But in practical, depending on the efficiency of the filter, it will not be allowed to cut all the frequencies below omega c. It will allow some portions below omega c. So that is one disadvantage of SSB, that for efficient SSB transmission, we need to design the filters very effectively using high cost. So this is one problem. Now the advantages of SSB, SC signal. The bandwidth efficiency. So when you are sending only upper sideband or lower sideband, you are only transmitting single sideband. So there is less requirement of bandwidth. So we are actually requiring half bandwidth of double sideband. Okay. So in case of double sideband, we require 2 FM frequency or 2 FM bandwidth. But in case of single sideband, we require FM bandwidth. So the bandwidth requirement of SSB is very less. Power efficiency. Power is very much safe because we are only transmitting one sideband. So power is safe in single sideband. Noise interference is low because the bandwidth is low. When the bandwidth is low, the noise interference will be low. Now vestigial sideband. What is vestigial sideband? So I have explained that in case of single sideband, the filter needs to be very high, the filter needs to be of high quality. Now, how to resolve this issue? Okay, so for designing a high pass filter, very high quality high pass filter, we need extra cost. But to resolve this issue, there is another way, which is vestigial sideband. Okay, now what is happening in vestigial sideband? In vestigial sideband, we are actually allowing one sideband, say for example, this upper sideband, and this lower sideband is gradually decreasing automatically. Okay, So in vestigial sideband, we are actually using some process by which this lower sideband is actually decreasing automatically. Okay, so when you will send this signal to a filter, so to remove only this portion of signal will be very much easier for this filter. So if we do not have a very high quality filter, then it will be okay for us, then it will work for us, okay, for this kind of scenario. So this is actually vestigial sideband, okay, and this sideband is known as vestige sideband. Vestige means which is decaying, which is decreasing gradually. Now let's see this slide. In vestigial sideband, the disadvantage of single sideband are overcome by transmitting either one of the two sidebands completely, and other sideband is vestigial in nature. Vestigial means it will be decreased naturally. Vestigial in nature means gradually decreasing, which leads to ease of filter designing, and bandwidth lies between omega m and 2 omega m. So when you are allowing some portion from the lower sideband, so the bandwidth will increase. So instead of FM, it will be a bit higher than FM, but lower than 2 FM. So it will be vary from FM to 2 FM. So the bandwidth varies from lies between FM omega m to 2 omega m. The time domain description of vestigial sideband signal is given by this equation. Okay. Now here XQT is a vestige message signal. The spectrum of this vestigial sideband is shown in the following figure. So using this signal, the lower sideband will automatically decreasing. Okay. Now this is the application of VSB. Now this is self-study. You will see that, see this slide at home. Now the advantages of VSB. So reduction of bandwidth than DSP. So the bandwidth is increased than SSB, but it is still lower than double sideband. Okay. Easy of designing sideband filter due to vestige nature of wave. So the sideband filter, okay, in case of designing the sideband filter, here the process is a bit easier here. Okay, so you do not need a very high quality filter in this case. It is low cost, good phase characteristic, and makes low frequency component transmission. Okay, so these are the advantages of vestigial sideband. Okay, so this is the end of week 4 lecture.